Today is going to be about when we should expect quantum advantage. What are the properties of quantum states that push them beyond the reach of a classical computer? And some kind of simple models for how we should understand the features of a quantum state that make it hard to describe. So the first part of this lecture is going to be introducing the notion of von Neumann entropy, or more generally entanglement measures. We'll then talk about how entanglement grows under generic quantum computation, and having discussed that, we'll then talk about how we can understand entanglement as a feature that is hard to describe on classical computers, and so a candidate for sources of quantum advantage. The next lecture will be about how it's actually a bit more subtle. So these are going to be two ways of thinking about human interpretable quantum states. But to motivate thinking about both of those, let's first talk about entanglement. So what is entanglement? So before we even talk about entanglement, I want to define entropy. So let's first talk about Shannon entropy. And since it's kind of a small group today, do feel free to jump in, ask lots of questions. Okay, Shannon entropy. So this has absolutely nothing to do with quantum mechanics. It's just basic information theory. So the question is basically, how much information do you need to store a signal from some random source? Okay, so imagine somebody sending you messages, 0 or 1, with different probabilities. And over a long period of time, you develop some long list of numbers that look something like this. So mostly they send you 0s, sometimes they send you 1s. And you want to know basically what is the information content of this message, okay? So if the sender only ever sends you 0s, there's kind of no information content in the message, right? Aside from the statement, it's all 0s. As you increase the length of the message, the kind of content is not increasing, right? But once there are some 1s in there is more information here. They can start sending you messages. So in order to introduce the idea of Shannon entropy, what we're going to ask is basically, how many bits of information do we need to store this string, okay? So in general, the idea is we have some string of observed messages. So these are our individual messages, or letters in our message. So here it could be 0, 1, it could be A, B, C, D, they could be pictures of cats. So the question is, how much does it cost to store this thing? So let's first think about this message, right? So what's a more efficient way to store this thing, if there are very few 1s appearing, is instead of writing down all of the 0s, we could just say, well, where are the 1s in the string, right? Instead of writing down the whole string, we could say, well, there's a 1 in position 5, and there's a 1 in position 8, and so on. Okay? So what we're going to need to describe the amount of information in a signal that's sent to us is the entropy. The entropy is going to provide a way for us to quantify the amount of information in this signal. So how much info to store string? So here, let's imagine that we receive the message X. With some probability, px, right? So there's a bunch of different x's in this string, and there's a bunch of some of the probabilities for all the different possible signals x has to be 1, right? So in order to quantify how much information is in the signal, we're going to want to define a function that has a few key properties. So that is to say, I want to define some f of x, which is basically how much info to record x. Okay, so we're going to want a few properties of this. So first off, we don't want the information required to store our signal to depend on the particular symbol we're using, right? So the information we need to store 0, 0, 0, 0, 1, and so on should be the same as the information we need to record A, B, right? Okay, so we want it to be label independent. that's our first criterion for defining how much information is in a signal. The next criterion is basically just going to be for convenience. So we want it to be a smooth function. And the last criterion is really the one that gives us the key constraint. Let's imagine that somebody was sending us two totally different signals, right? So they send us a string of vectors like this, and then they send us an uncorrelated message. The amount of information we need to store two totally uncorrelated messages, we would like that to be the sum of the information required to store the individual messages. So for x and x prime uncorrelated, we would like f of x plus f of x and x prime to have this property. For uncorrelated, or rather for independent x and x prime. Okay, so this last one is really the thing that constrains us, right? So we want f of x that depends on p. We want it to be smooth, and we want and let's just be clear. So if we have two uncorrelated messages, the probability for x and x prime is the probability for x and the probability for x prime, right? Okay. So under the condition that the function that counts the amount of information required to store the symbol x being just the sum of the individual terms, another way of saying this is that we want f of p of x prime to be f of p of x plus f of p of x prime. So you can see what's happening here. The point is that this is going to imply that the amount of information necessary to store, I'll put that in square brackets because I'm getting a bit sloppy with notation, but the point is the information required to store the symbol x should be something like this, right? It should be a logarithm of a number. Because if it's a logarithm, then when we insert the product of probabilities into here, we get a sum. Okay? And so we're going to do two things. So let's just like, for now, we'll choose to record entropy in base 2. And also we're going to set k equals 1. Okay, so f of x is this is the information required to store a particular signal, but now, sorry, a particular kind of letter that we received. And then because we receive each of these symbols in this string with some probability px, that means that the kind of the average information to store a signal it's just the sum over all the different possible x's we could get, the probabilities, and then f of x. But that here is just this thing. And this is what we call the Shannon entropy, right? So many of you will recognize this object as the Gibbs entropy in statistical mechanics, right? So this thing here is Shannon entropy. Okay, so why are we talking about this classical information measure? The reason we're talking about this classical information measure is it's going to motivate the definition of the von Neumann entropy, which acts as an entanglement entropy. So another kind of really remarkable fact about this, and this is going back to Shannon's work in the late 40s, is it tells you about basically the number of bits required for the optimal lossless compression of a signal. Okay, so imagine somebody is sending you a signal of this kind, where say 0 is more likely than 1. If it was all zeros, as I mentioned before, you really don't need much information to store this whole thing. You can just store it's always zeros. So the idea is that you can compress a given signal you receive into a smaller number of bits. And h of p, the Shannon entropy, is essentially telling you how many bits you need. Okay? So let me just write that down over here because it's pretty key property. So the idea is with a length n signal, i.e. like x1 going up to xn, with each of them independent. So we have some probability of getting x1 and then a probability of getting xn. The idea is we can compress this length n signal The idea is pretty simple. So what you do is you say, let's say you have an extremely common symbol, say 0. You give that you want to represent that with as fewer bits as possible. Why don't we just say that we represent 0 with no bits at all, right? So every time there's a 0, we use no bits. Whenever there's a 1, we use some longer symbol. So a key example that I mentioned a moment ago is one way of compressing the signal that is non-optimal, but still gives an example of a compression, is where you never write down the zeros and you just write down the locations of the ones. Okay, so that's one way of like shortening your bit string from the thing that you've received. Okay, so H of P is the Shannon entropy. We can think of as the definition of the information content of a signal, okay? So having defined the Shannon entropy, we're now ready to introduce the von Neumann entropy, which is going to allow us to describe the information content of density matrices, and so of quantum states. So I'm going to move over to the left side here. So the idea is, again, going to be pretty simple. So now imagine you have some density matrix, rho, for some number of qubits, doesn't matter how many. Let's write down its spectral decomposition. So the spectral decomposition of any density matrix can be written in this form. Let's call this psi of x. Okay, so this is just the spectral decomposition. So these are the eigenstates of rho, and these are the eigenvalues of rho. And now the key property of the density matrix is, of course, the trace of rho is 1. And so, of course, as we mentioned already, you can interpret these as probabilities of individual events. So, okay, how do we apply this reasoning over here to the von Neumann entropy? Now, okay, let's imagine somebody sends you information, but they send you information not in the form of bits. They send you quantum states, right? So imagine somebody is sending you states, psi of x, according to some probability P of x, okay? And now what you do is when you receive one of these states, you measure in the eigenbasis. So when you measure in the eigenbasis, that is to say you measure an observable that has the same eigenvectors as rho, but maybe let's say the eigenvalues are distinct, so you always get a distinct result. They send you these signals drawn from rho, and then the entropy of the kind of signal that you've received, the Shannon entropy of the signal you've received, is just going to be the Shannon entropy of this distribution of px, okay? So here, the von Neumann entropy, this is what I call von Neumann, or Vn, the von Neumann entropy of rho is just this thing which looks at the Shannon entropy. But the key point is that we can of course write this in a way that is basis independent in terms of the density matrix. Okay, so this log of the density matrix should be understood as defined from the spectral decomposition. So the log of the matrix is the log of the eigenvalues with the same eigenvectors. So this is our definition of von Neumann entropy. Okay, so what does it have to do with entanglement? Okay, so to connect the von Neumann entropy to entanglement, it's going to be useful to think about some big pure states, right? So when we think about some overall pure state of some huge system, then what we're going to want to do is basically ask how much information about this state is stored locally. Actually, let's start with a small system to give you a quick example, right? Let's imagine I have like a bell path. So I have like single qubit over here. So this is a bell path. So, it's like a singlet state. So let's say I have this bell path. Something kind of interesting about the bell path, first off, is the whole state is definite, right? The whole system is in a definite pure state. But a subsystem, of course, is not in a definite pure state. So let's say this is A and this is B. The reduced density matrix of a subsystem. Sorry, let's call this psi. So we can write the reduced density matrix in this way, okay? Okay, it's definite pure state, no entropy, right? So if we have a pure state and we calculate the von Neumann entropy, then we see that only one of these p's is non-zero, okay? If only one of the p's is non-zero, then you can see, okay, imagine taking p to 0 in this term here, you find 0. So the point is that S of psi is 0. But here S of rho A, it's log, yeah, I'll do this explicitly. So it's going to be 1/2 log base 2 eigenvalues of this thing, and then there's 2 of them with the same value. So we get log base 2, 2, 1, okay? So our maximally mixed state, which is the state of one of these qubits, has entropy, right? What I want to stress is that this is this example already is showing you something pretty weird from the perspective if you compare it with classical information measures, okay? So classical information measures are telling you about the uncertainty and they're kind of the amount of information that's required to describe a probability distribution. And the key point, a kind of key feature of the Shannon entropy, or a key feature of classical distributions, is that the amount of entropy of a system is no smaller than the entropy of a subsystem, okay? This is a really key property. So in quantum mechanics, we can have a von Neumann entropy, S of rho A, that is greater. This is allowed. This isn't like definite, this is possible. So we can have a von Neumann entropy of a subsystem A that is larger than the von Neumann entropy of a larger system. This is not the case for the Shannon entropy. What this is basically saying is that in this state, there's no local information. If you look at a single qubit, there's just no information at all. The state of this qubit, this single qubit on this side A, is stored elsewhere. The information is stored non-locally across A and B. So what we'd like to do is quantify that idea. We want to ask basically how much information about a subsystem is stored outside of that subsystem. So let's look at a general pure state. So let's say we have some larger system, A and B, and let's say there's like NA qubits here, and there's NB qubits here. And now we have some state psi of AB, which is like N equals NA plus NB qubits. And to quantify the entropy in psi, well, okay, first off, as before, S of psi, well, really the density matrix, this is going to be 0. I'm going to just talk briefly about something called a Schmidt decomposition, which is going to tell us something about the reduced density matrix, okay? So if we have some big state here of AB, we can write this down using a complete basis of the left system and the right system. Okay, so this is a basis for B. And this is a basis for A. And the first thing, of course, if we have multiple states here, it looks as if the state is going to be entangled, right? But we want to make that a little bit sharper. So a way to see the entanglement in this state is to perform a Schmidt decomposition. So a Schmidt decomposition, which is a really key idea in quantum information, the thing is, it's really just a singular value decomposition, is the following. So what we want to do is basically change our basis on A and on B to reveal the entanglement that is there between A and B. And in doing this, we're going to find out that a feature or property of the Schmidt decomposition is very closely related to a property of the reduced density matrix. So the idea is basically this. So let's take this state psi, which we can think of as a rectangular matrix, right? So we can think of this thing here as some 2 to the NA by 2 to the NB matrix. Okay? So previously it was just a bunch of amplitudes. Now let's think of it as a rectangular matrix. Now let's write down the singular value decomposition of this thing. And now the singular value decomposition has this form. Right, I'll stick to the same notation in the notes. Let's call that little a. That's b. So this is the singular value decomposition. Every matrix has a singular value decomposition. Okay. And so give that a dagger. So these two are isometries. They're like rectangular unitaries, and these are the singular values. These are the singular values, but in this context, we call them Schmidt values. Okay, so the point is that after doing this, what we've done is we've moved to a basis where the state takes a much more, well, a much simpler form. So, okay, let's move back over here. So for any quantum state of a bipartite system, I can always perform the Schmidt decomposition of the wave function amplitudes. And after I perform this Schmidt decomposition, you can see that what's happened to the state is that we've written it in this form. This is literally just taking the singular value decomposition and inserting it into the expression above. Okay, and so let's write this thing as, what do we call it here? A of A. A of B. Okay, so there are some really important properties of this expression that we should talk about. So these things I mentioned there, they were isometries, which is basically to say that U dagger U is equal to V dagger, well, it's equal to the identity on A, and V dagger V is also the identity in different spaces. So what these properties mean is that when you perform the singular value decomposition of the wave function amplitudes, is that you end up with these vectors here, which are mutually orthogonal to each other, okay? So there's only one sum here, and we have that A in subsystem A, times another, B is just another one of these states. And similarly, okay, so the point is that this thing is like the generalization of an EPR pair, right? Where we've changed our weights. So our Bell pair or EPR pair was just a sum of orthogonal tensor products. And here we've ended up with the same thing. So sum over orthogonal tensor products. So the point is basically that if you have, okay, clearly if you have only one non-zero singular value, the state is unentangled. If you have many non-zero singular values or Schmidt values, these sigmas, then the state is going to be entangled. And then the kind of final point to connect this to the von Neumann entropy is after doing the Schmidt decomposition, you can see that the reduced density matrix of A, the reduced density matrix that we get from tracing out B, if we just insert this expression into it, we get something really simple. It's just this thing. Okay, so the singular values of the quantum state are the Schmidt values of, sorry, the singular values of the quantum state squared are the eigenvalues of the reduced density matrix. Okay, and so that means that the von Neumann entropy is just a function of these singular values. So what this means is that the entanglement between A and B, as quantified by the von Neumann entropy, is basically quantifying the entropy and the distribution of these, the distribution defined by these singular values. Okay, so that's a kind of crash course in entanglement entropy. Now let's talk about something that's not in Nielsen and Schwong. We're going to talk about something a bit more fun, which is the so-called minimal cut argument formulated just under a decade ago by researchers working on quantum dynamics. Okay, just kind of summarize this part. This is entanglement entropy. It's a way of quantifying the information that is stored non-locally in a quantum state. Soon, we'll also see that it describes is related rather to the amount of classical memory that's required to represent the state on a computer. One way of seeing that is basically to say, well, if I have lots of different singular values here, then I need to represent lots of different states here, right? If I have only one singular value, I just need to store one state on the left and one state on the right, and not much memory is required. More generally, the number of non-zero Schmidt values is going to be very, very closely related to the classical memory required. So what that means is lots of entanglement, lots of classical memory, a potential for a classical computer to break down, and therefore for a quantum advantage. Okay, so any questions so far?
What's the chance you don't for classical information. The is tells you like how much a signal can be compressed. So what's the like analog and the quantum version? There is one.
Yeah, so I mean, one thing you can do is just like directly apply Shannon's noiseless coding theorem and say, imagine somebody is sending you there's a density matrix which describes kind of average over different pure states you could be sent, and they keep sending you this density matrix, or rather you're given the same density matrix many times, and then you perform a measurement in an orthogonal basis which happens to coincide with the eigenbasis. Then what you do is you just get signals at exactly the same rate. So that's the kind of clearest relation there. Any other questions so far? Okay. Okay, that's entanglement entropy. Now let's talk again about quantum computation rather than quantum information. So last lecture we talked about quantum circuits. I showed you how to construct some simple quantum circuits, or or maybe some sophisticated quantum circuits using simple unitary gates. Just these C-naughts and single qubit unitaries. So what we're going to want to do now is basically ask, well, what happens if I run a generic computation? Okay, what is the kind of quantum state that emerges generally when I just take a bunch of qubits in state 0 and I start acting on them with these local gates? So the picture we're going to build towards over this lecture and the next one is this idea of, I guess I'd call it uselessness of quantum states. And it's going to be a step towards understanding why it's so hard to get quantum advantage. Okay, so here's the basic idea that we're going to go over. Here's Hilbert space. Okay, n-qubit Hilbert space. This is some 2 to the n dimensional space. In this 2 to the n dimensional space, there are some things that we can write down, right? So we can write down like the all-zero state. This is something in Hilbert space. Another thing that we can write down in Hilbert space is 0, 1, 0, 0. Another thing that we can and so on, right? There are these like human interpretable states, which are what basically essentially classical states, or states that have efficient classical representations. So what we're going to see now is actually when you start evolving a quantum system under some series of local operations, generically what happens is that the states wander off into the kind of highly entangled core of Hilbert space. Okay. So we're going to start from simple states. Almost anything we do is going to take us off into some very highly entangled state that we can no longer represent in a classical computer. So almost every state, you just can't write it down. The next lecture is going to be about, that is basically to say, like, it seems that if you describe your task loosely, let's say our task that we want to do on our computer is to represent a very complicated quantum state, then clearly the quantum computer can do that, right? A quantum computer, as I'll describe in a moment, very naturally takes us off into this like soup of highly entangled states. And so if that's all the only task we want, clearly there's an advantage. The classical memory required to represent one of these states is exponentially large in the number of degrees of freedom in general, as we'll see in a moment. So before I go on to why that's not such a useful task or not such a useful idea, what I first want to explain to you is why it is that we should expect to wander off into this like soup of highly entangled states. Kind of the punchline next lecture is going to be that most of them are useless, right? But we want to know why we get there in the first place. Okay, so this is going to take us into something called the minimal cut argument. So what do I mean by a generic quantum computation? So let's go back to our circuit diagram. Okay, we've got a bunch of qubits here. This is like time. And we'll start off in the 0 state. And what I'm going to do is I'm going to apply some unitary operation. So a single qubit unitary operation is going to turn out to be pretty boring. So let's just draw, we can just merge those into the 2-qubit unitaries. And I'm now going to draw those like this, okay? So this thing here, you could think of it as something like a C naught, and then like a single qubit unitary, and then some other single qubit, maybe another C naught, maybe like something crazy like this, right? This is some example of some 2-qubit unitary operation. So we're going to take our quantum system and we're going to start evolving it under these 2-qubit gates. So the question is basically whether we can make any statements about the states that generically arise from these operations. So, and this leads us to the minimal cut argument. So here's the basic idea. So what I want to do is to understand in a bit more detail the structure of a Schmidt decomposition. Okay, so out here I get some state psi. And what I'm going to do is I'm going to chop my system into two parts. So this to be clear, this is the minimal cut argument, described much more elegantly and originally in Nahum et al. With the references in the notes from 2017, the PRX. So this is going to show us how entanglement grows. So let's divide our system into a region A and a region B. So everything else is B. Okay, and what I want to know is how entangled psi is across the cut between A and B. So we'll write down the same expression that we had before. We have some states in A. We have some states in B. And the point is that the structure of this network of gates, the structure of the fact that this circuit is generated by just a bunch of kind of local 2-qubit operations, is going to mean that we know quite a bit actually about the Schmidt decomposition of psi. In particular, what we're going to be able to do is to find an upper bound on the number of non-zero Schmidt values, and therefore the number of non-zero eigenvalues of the density matrix in A. That upper bound on the number of eigenvalues is then going to provide us with an upper bound on the von Neumann entropy of this system. So here's the basic idea. So let's take this circuit and try and break it in two. So here's actually really simple. Okay, so okay, let's ask lots of questions about this drawing because I found this almost impossible to describe without detailed drawings in the notes. So what I want to do is, okay, I'm going to draw almost the same circuit and I'm going to cut it. Okay, I'm going to draw exactly the same circuit. I've got enough lines. But whatever. Okay, so let's it doesn't matter if it's exactly the same. So okay, this is A, and this is B. So what I want is like a way of representing this tensor network as a sum over fewer terms. So what I want to do is I'm going to imagine a cut through the system. Okay, so I take my scissors and I'm going to imagine going through my circuit and cutting these legs in this tensor network, right?
Is it important that we lost one of the keys?
No, yeah. So the argument I'm going to make here just applies generally to quantum circuits. So imagine you take this circuit and try and imagine cutting through here. Now, what do I mean by cutting? So let's think about what each of these connections means, right? So when I write something like this, let's just look at this 3-qubit state. When I write something like this, what I mean, let's call this U1 and U2, let's say, and this is 0, 0, 0. And what I want to write down is like the wave function amplitude, right? So maybe let's call this like I1, I2, and I3. This is psi I1, I2, I3. Okay. When I write something like this down, I have an internal sum. Okay. So this represents a sum over some internal variable in the tensor network. So explicitly, I can write down this wave function amplitude in the following way. Okay, so I've just introduced a resolution of the identity here. So this thing here, it's like, you should think of this thing with the sum over j as like, I've just taken the identity operator and added it into the circuit, but I've written the identity in this way, like a single qubit identity. Okay, so I've taken my quantum circuit and it looks like I broke it into two parts, right? You can see now that whatever's going on in A, it's in a product, like in each of these terms, I have a product state. So here I have a sum over j, and now so if this was like B and this was A, what I now have is a sum over j and then some unnormalized state of B labeled by j, tensor product with some unnormalized state of A labeled by j. So I flip the order of the tensor product. So this is a really key point. So let's pause for a moment to discuss this. I'm taking a quantum circuit and I'm throwing a resolution of the identity in it and summing over the different basis states for that single qubit resolution of the identity. In doing that, what I've done is I've kind of broken the system into two parts. I've cut it into two pieces. Okay? So the idea is basically that the number of internal indices that you have to sum over in the circuit is going to tell us about the singular value decomposition or Schmidt decomposition. So the next point is that the maximum possible number, sorry, is there a question?
Yeah, so just to make sure, so 5B superscript J is just the output of the first two qubits after U1, but where the second qubit has just been projected into the J basis, basically.
Yeah, so B is now just a one qubit state. So actually, I'll write these down explicitly in terms of these unit theories. That's probably going to make this a bit clearer. So yeah, I'll just give you an example of what psi 5B is. So 5B J is coming from, it's just this state on this qubit. So I have like U1, and then there's some degree of freedom here. Let's call it as I1 J. So this is like I1. So I have I1 and J are the output. And then these are the kind of column, these are the row indices and these are the column indices. And then I have this thing. So this thing here is 5BJ. Okay, the key point is this is a product state after I've inserted this resolution to the identity. So cutting a circuit in my language just means inserting resolutions to the identity and keeping track of how many terms are in the sum. The key point is that if we have only two terms here, as we do in this case, the maximum possible number of terms in the singular value decomposition is also 2. Okay, so let's focus more on this central diagram here. So here's the idea. You imagine this cut through the circuit. Okay, one cut the circuit. How many resolutions of the identity do you need? Okay, so in this case, in order to cut the system into two parts, we need to cut this leg here, and we need to cut this leg here. Okay, so to chop this thing into a product state over here and a product state over here, two cuts. Each of them is a resolution of the identity in a qubit system. Each has two values, right? So I have to sum over two different basis states here and two different basis states here. So what that means is that, so the point is that this is equal to the number of cuts. And so then how many terms in the sum? I.e., when we now write psi as a sum over some unnormalized states of A and B, where now J here is like all internal indices. the number of terms that we have to sum over is 2 to the that number is equal to 2 to the number of cuts. Okay, so this is a prescription for taking any quantum circuit and just asking, well, what's the minimum number of ways that I have to cut the system in two? Okay. So then the next part of the argument is going to give us our upper bounds on the entropy. Are there any more questions before I proceed? Because this, I think, takes wrapping your head around a bit. So what I'm doing is I'm taking tensor networks, I'm just trying to rip them in half.
Why do we have to figure it out?
Lower bounding is more difficult, and I'll talk about it next time. So I'm talking about this because it's going to give us a it's going to tell us something about this, something called the Hartley entropy or the Renyi zero entropy, which is going to be more closely related to the memory required in a classical computer. The minimal cut argument is, however, the thing we're focusing on because it's so simple.
But I guess if we're trying to show that things are highly enabled, so we want to
Yeah, we would like, you're right. Yeah, I totally agree. We would like to get a lower bound on it. So what I'm going to do is I'm going to show you an upper bound, and then I'm going to tell you that there are other more sophisticated calculations that give you a lower bound that scales in the same way. So what I'm going to show you is that the upper bound, I'm going to show you how the upper bound scales with circuit depth. And I'm just going to tell you that there's a much more complicated calculation you could do that will give you a lower bound that scales in the same way. So the upper bound is, however, going to be, it's generically going to be, the upper bound we get is generically going to be exactly equal to the true Hartley entropy, which is going to tell us the true so-called bond dimension we need in a tensor network. So its value is going to be more its relation to tensor network calculations than anything else. And that's what's important for understanding breakdown of classical computation. Any other questions? Okay. So I'll keep this picture here. Okay, so having determined the number of terms in the sum, the point now is that when we write our state psi, which lives over here, in some singular value decomposition, so the number of Schmidt values not equal to 0 is less than or equal to less than or equal to 2 to the number of cuts. Okay. So we had 2 to the number of cuts terms in this sum. The best we can possibly, but so the different states here are not necessarily orthogonal. That's the key point. So because the different states here are not necessarily orthogonal, then the number of singular values could actually be smaller than 2 to the number of cuts. But if they happened to be orthogonal, this would already be a Schmidt decomposition, and then we would just get that the number of non-zero singular values was equal to the number of cuts. Sorry, Schmidt value and singular value, just to stress that I'm using them in exactly the same way. It's the singular value of the decomposition of the matrix representation of psi, which we call a Schmidt value. Okay, so now we get to okay, why is it called minimal cuts? Now we see it pretty easily. The point is that what we really want to know is the number of non-zero Schmidt values. That tells us something about the entropy. And we had lots of freedom in how we did this cut, right? So, but it's always an upper bound. So if we just find the cut, if we find the minimal cut, if we find the path through this circuit that cuts the fewest legs, that's going to give us a better upper bound. Okay, why do we care about this? Now let's go on to an upper bound of the entropy. So yeah, I'm going to define something called the Hartley entropy. But it's okay. I don't know the origin of the name. I've mentioned somebody called Hartley came up with it. It's defined in this way. The key point, and this is, I can leave you to convince yourselves of this, but this thing is greater than or equal to the Renyi entropy, sorry, the von Neumann entropy, which is minus sum of a sigma a squared log sigma a squared. Okay. So now we see that we can upper bound the von Neumann entropy with just number of cuts. Okay, because we had 2 to the number of cuts here, logs are defined base 2. An upper bound on the von Neumann entropy of a subregion given by just the number of cuts in this circuit. Okay, so now we get to the kind of key point. Let's imagine that we were running a quantum computation for a time t, right? So we evolve for a time t. Every step we apply gates kind of all on a bunch of our qubits. We can do operations in parallel. That's of course you want to do that if you want to do an efficient quantum computation. And the point is that the number of gates applied is basically going to go like the number of qubits times the time that you run the whole thing for, right? So you can convince yourself pretty easily that if you do this and you just throw these gates down randomly, the number of cuts you're going to have to do if you're throwing these down all over the place in an uncorrelated way is going to be proportional to time, right? So if I made this very, very deep, then in order to cut the system into 2 pieces, I'm going to have to cut a number of legs that is proportional to the depth or depth of the circuit or the time that I run the whole thing for. So what that means is that the number of cuts here is proportional to t. And so this is, well, I don't need to write this part again. The point is we get an upper bound on the von Neumann entropy that's going as t. Okay, so now the last thing I'm going to comment on, fairly briefly, is what this means for our pursuit of quantum advantage. Like, where can we find quantum computers? When can we find things that quantum computers can do that classical computers cannot do? So, a basic criterion for quantum advantage, or basic criterion for a quantum computer to be more useful than a classical computer for a particular task, is that the classical computer is really bad at it, right? Like, the quantum computer can do something that the classical computer just is awful at. And the point is that if a state is very highly entangled, it turns out that through a tensor network representation, it costs a lot of memory to represent. So let's just get to that point now very briefly. Yeah, I'll wrap up within the next 2 or 3 minutes. Here's the basic idea. Let's stick to like a one-dimensional quantum computer. Keep things extra simple. So yeah, I've been writing quantum states like this, right? Like I2 up to IN. I can write them, I can make all the coefficients explicit. And the point is that this thing is a rank n tensor. Right? It's like the n-dimensional hypercube analog of a matrix. So one way of drawing these coefficients, and it's terrible. One way of drawing these coefficients, never mind. Is like this, right? So I'm going to it's a big matrix, and I'm just going to represent the legs of the tensor. Like this, okay? There's like many legs here. So in this representation, like a matrix that you're more familiar with looks like this, right? And a vector looks like this. So this is a rank n tensor. So the point is that there exists a decomposition, which is basically many SVDs. So I'm just going to basically what I'm going to do is a Schmidt decomposition across this. And then after doing a Schmidt decomposition across that, I'll do another. So what I'm going to end up with is something that looks like this. So you can think of this thing as like the U in the SVD. And then these are the singular values. And then this is like the V in the SVD. And then I'm going to do it again. And again, and so on. Okay? This is described in detail in the paper from Guthrie-Vidal that is referenced in the notes. The overall point is that if you have a quantum state, and it has a natural 1D structure in this case, then you can break it down into a representation that requires an exact representation, requires memory that goes as n, the number of qubits, multiplied by 2 to the S0 squared. So this is called, this thing here, chi, is called bond dimension. Okay, so what this tells us is that if we have entropy growing linearly in time under generic computation, then the memory required to represent this quantum state grows exponentially in time. Okay? So this is time, this is memory. That's an exact representation. An approximate representation is more, the relevant quantity is the von Neumann entropy or something called the Renyi 2 entropy we can talk about later. So this is the basic point. So okay, if you want your classical computer to break down, and so you want to enter a regime where only a quantum computer is going to do anything, easy thing to do is just to run a totally generic evolution, right? A totally generic sequence of gates is going to quickly take you into a regime where your classical computer breaks down. So this is, let's say, this is your 1 Avogadro of bits that you have in the world. You're going to hit that 1 Avogadro of bits at a time that is, well, it's going to be about 70 steps. So at this point, you're dead, right? So this is kind of weird, right? This is basically to say that generic quantum states are not human interpretable beyond a certain depth. And so, yeah, that's the, okay, so that concludes our discussion of entanglement. The idea then is basically that we have simple quantum states which under generic unitary evolution wander into this like totally uninterpretable part of Hilbert space. In that part of Hilbert space, the quantum computer can clearly do something that the classical computer can't. In the next lecture, what we'll talk about is how most of the states you end up with in that kind of entangled soup in the middle of Hilbert space are totally useless. Like you can't extract anything from them. And after understanding that feature of quantum mechanics, we're going to have a pretty strong motivation to start thinking in more detail about more structured quantum algorithms, which are going to be very specific paths through Hilbert space that take us through the kind of entangled center into states that are still human interpretable. So that's our route. So just to kind of draw a picture to wrap up this lecture. Here's Hilbert space. Let's say here are states we can represent on classical computers. Let's call it human interpretable. Everything out here, mostly nothing, okay? There are these particular structured paths through Hilbert space. Useful entangled states. So Shor's algorithm you can think of as such a path, and Grover's algorithm is also such a path. So basically you want to follow these trajectories, but if you're not too careful about it, you are going to quickly wander into a regime where the classical computer, it's useless, it can't do anything, but out here, this is just like a mess. In that we're not going to be able to extract any information from it at all in less than exponential time. And so that's next time. So thank you all for listening. And yeah, I'll see you next Tuesday.